Hello everyone, Aaron here and welcome back to Leetcode. Today we are doing the insert delete get random order 1 problem. Very catchy. Implement the randomized set class such that randomized set initializes the randomized set object. Makes sense. Insert the value returns a boolean. This inserts the item val into the set if it's not present. Return true if the item was not present, and thus must have been inserted, or false otherwise. Remove the value from the set if it's present. Returns true if the item was present, false otherwise. GetRandom returns a random element from the current set of elements. It's guaranteed that at least one element exists when this method is called. Each element must have the same probability of being returned. You must implement the functions of the class such that each function works in average order 1 time complexity. Okay. Let me just... okay. Okay, so my immediate thinking is we have to be time efficient, we don't have to be space efficient, we can be pretty wasteful here. How can we do this? Well, okay, almost all of this is very, very similar to a Python set. So self.items is a set. Insert something into the set. If val in self.items return false, self.items.add val return true. Remove if val in self.items.remove val return true, return false. That leaves getting a random element. How do we want to do this? So in Python, you can't just index a set. It's simply not a thing you can do. That's because they have no order as such. You can't, well, in recent Python version, I don't think you can index into a set. I'm actually slightly interested now. In fact, let's try it. I was going to say you can't index into a set. But maybe you can. So random.range is a Python function that just gives you something between 0 and this number minus 1. So the same as a regular range gives you between 0 and n minus 1. This gives you, a regular range gives you all of them. This one gives you a random one of them. Can you index into a set? I don't think you can. So the reason I'm suddenly unsure, random has no attribute range. Maybe that's in a different version of Python. Maybe we need to do randint or 0 and len items minus 1. So range may have been added later. Okay, set object is not subscriptable. Right, so the reason I was unsure was because traditionally Python sets are unordered. you don't know what order the elements are going to be in the set. That's slightly changed in more recent versions of Python in that they're guaranteed to produce the same order that they're added. So that made me think maybe you can index them, but no, you can't. So I'm thinking self.indexable items can be a list. Now the remove, actually we need to be more clever. Maybe we don't make this a set. We make this len self.indexable items. And then it's going to be index self.items for a value. We'll deal with the rest of that later. And then del self.items value, remove it from the dictionary. So now we generate a random index into this, and that will effectively remove our no, sorry. This does a. We'll come back to this. So this generates a random index into the indexable items. Lists are indexable, so we know that's fine. The problem is we don't remove the element up here. What we could do is self.indexable items.pop index. So now that works. The problem is this is order n. So how can we make sure to get rid of this? Maybe this isn't what we want. Maybe we actually want another dictionary. Let's do an index is this. So basically what I'm trying to do here is I'm trying to make an array that I can delete from quickly. And one way to think about that is it's a dictionary from integers to values. A list is basically a dictionary from integers to values, with the special property that the keys are always consecutive. Now, this effectively removes that property. So that I could have, for example, 0, 2 as the keys in my dictionary, as in my indexable items dictionary. But I think that's kind of okay, because I just want random.choose, or is it random.choice? Could be choice. I can never remember which way it is. Yes, I did mean choice. So the reason I always get confused is because there's itertools.choose, I think it is, something like that. Dict keys object is not subscriptable. Ah! How can I... I don't want to turn the keys into a list. because that's going to take order n time. What I was hoping to do was basically just randomly pick one of the keys. So if Python's sets were random, as in randomly ordered, no, it doesn't meet the guarantees of this. Okay. Let's quickly fix this just with a list. But this isn't right. This transformation here costs order n time. So our random choice is order n. This len up here is not order n, it's order 1 because arrays must store their length. The lists must store their length. If it was a linked list, that would be order n. What am I not getting here? Because there are other options. We could go back to storing this as a list, and rather than removing elements, fill them with, say, a null, or a none, sorry. And then one option is to just re-roll our random index until we land on something that's not order, not none, but that can, well, that's entirely unanalyzable. There's really no good way to give a bound for that. What we could do instead is do a roll then slide. So if we have, say, 0 filled, 1 is none, and 2 is filled, we could, if we rolled a 1, we could just slide onto the 2, but that destroys the same probability requirement. And it also makes it potentially order n. The reason it destroys the same probability argument is effectively now you've got 0 has a 1 in 3 chance of being picked, and 2 now has a 2 in 3 chance of being picked, because if you pick a 1, you implicitly choose the 2. So we can't do that slide technique. Can I... It only needs to have an average of 0.1 time complexity. So which of these can I sabotage every nth call, for example? I don't know. I'm a bit stuck here. How can I do this better? Given a key... Well, we can do the unanalyzable way. I equals none. While I not in self.indexable items, I is equal to rand... No, I don't actually know. Ooh, this is actually wrong in really subtle ways. So that's actually quite bad. I think what I want to do is go back to this, but rather than do this, I just want to do our none tombstone. Let's go back to random.randint len self.indexable items from 0 to the length -1, while self.indexable items I is none. Keep trying. Now the danger here, of course, is that this just gets stuck in an infinite loop. And in fact, it will get worse. It will get worse as time goes on, because as we remove more items, we end up with more and more nuns. So what we can do is keep track of some vacant indices. If self.vacant indices is, if there's a vacant index, we want to do self.vacant indices pop. So I can take a random element from a set. That's fine. So what this does, it says if there's something that we've marked as none, self.indexable items.append none. So if there's some space we've previously turned into a none, we will set that. Then fill it. Otherwise, make space on the end and fill that. So down here, what we want to do is do self.vacant indices.append add index. So mark this as a free spot. So now this should work. We are less likely. Okay, we can still end up in a bad state. In that, if we add a whole lot of items, then remove a whole lot of items, we can end up with most of it being nuns. Is that likely? They'll probably test that. What we should do we should probably check that if the number of vacant indices exceeds the number of items, we should probably just re-index everything. That's obviously very expensive and will take order n time, but it shouldn't happen very often. You would have to have done a whole lot of inserts and a whole lot of removes to end up in this situation. In fact, you'd have to have done order n of them approximately. So it's order n work, but we're only going to do it one every order n times. If len self.vacant indices is greater than or equal to len self.items self.compact. Right. What we want to do is effectively for... How do I want to do this? What I want to do is I want to take the items. I want to take their values. No, the keys, in fact, because we're storing them in the keys. Items is equal to self.items.keys. In fact, I want to turn this into a list specifically. For index item in enumerate items. Oh, and I want to purge self.vacant indices gets reset to a set. Self.indexable items is going to turn into len item. And in fact, that's going to be items. And self.items is going to be item index for index item in enumerate. Self.indexable items. I think that works. So the complexity of this is this takes order n time, this is instant, this is order n time. So that's order n overall, but we're only going to do it when the number of vacant indices exceeds the number of items remaining. So this order n work is only going to happen after we've done at least... Well, for that to be true, we have to have removed at least half the number of elements we've added. So that's order n as well. And what that means is that this never drops below 50%. Well, sorry. The odds of generating an index that's bad is never more than 50%. So we should expect to generate a good index fairly quickly. I'm not sure I can do any better than that. It's this probabilistic argument I do not like, but I really don't know how to do better. Because if I call compact every time we call GetRandom, that's order n work every time. That's too often. So this condition here is what keeps us fairly cheap. Well, asymptotically cheap. What the heck, let's submit it. We'll find out if we get hammered in the tests for being too slow. We were not too slow. How tight it was, I don't know. It may have loose enough bounds that you can get away with non-order n solutions. It's just whether this is order n. That's the big debate. It's really quite tricky to know what to call this. And I can't remember how to do analysis of probabilistic algorithms properly. We can consider this as a Bernoulli distribution, effectively, because it's a fixed probability. It never falls below a half. Sorry, it never rises. The odds of being bad never rise above half. Yeah, the odds of you getting a long string of bad rolls here is very, very low. 1 minus p to the k for some k. I'm happy with that. Anyway, I could stand here and stare at this and not make any progress on this particular analysis for a very long time. So let's not do that. Let's leave it here and go, it seems to be good enough to pass the tests. Anyway, that's going to be it from me. Do remember to like, comment, subscribe, all this good stuff. In particular, if you know how to do this analysis, or you have a better way of getting around this selection problem. If it didn't have to be uniform, I know how to do it. If it didn't have to be order 1, I'd know how to do it. But it's that combination of things that's really stumped me here. So do let me know in the comments if you know how to do it. That's it from me. I will see you next time.